My name is Brian Ranero. I'm a developer advocate at MongoDB, so my duty is to work with the community and help people understand how they can use MongoDB and field questions and perform webinars to help people understand how the system works. Today, we're going to be talking about MongoDB and Hadoop, using them together via the Hadoop connector that we provide as well. So let's go ahead and let's dive in so that we're not wasting any time and talk about what Hadoop actually is. So Hadoop is a system, a framework, or a set of libraries for processing very large data sets across distributed systems. The idea here is that we're going to have a great deal of data that we have accrued over time in the terabyte to petabyte size, and we want to perform analytics against that data. The type of analytics that we can perform is varied, but the problem that Hadoop is trying to solve is that we need a way of processing this massive amount of data in a reliable and efficient way. Now, Hadoop, part of the framework of this execution system, is going to be coordinating the efforts of many commodity servers together to perform this processing. We might use Hadoop for what is known as data warehousing, that I've called all of the data that I've ingested from my business, from upstream databases, into Hadoop, and now I'm going to perform some processing against that to get some understanding about what the data is trying to tell me. And this is the advanced analytics that we're going to perform from Hadoop. But it's important to understand that Hadoop is a very specialized kind of tool. It's not a database. People sometimes get confused about it being a massively scalable database. Some tools allow you to think or look at Hadoop like a database, but it's really about processing offline data in an efficient manner, and of course data that's very large. There's no indexing in Hadoop, so it's not really built to be queryable the way that we understand a database to be. This is more about batch processing. This is more about going across the entire data set and deriving some kind of insight from the data without necessarily changing or performing CRUD operations against that data. So a lot of static data. In my travels as an engineer and a consultant and a training person, there is some confusion about whether or not MongoDB is a competitor or a competing technology with Hadoop, and they are not. MongoDB is a database, and it serves a different kind of data management strategy than Hadoop does. But what's interesting about these two technologies is they can and do work very well together in a complementary fashion. To understand how, we can examine the different things that they do, and I apologize that slide didn't quite render perfectly. The idea with Hadoop is that it's a system that we're going to be processing data over large distributed systems, so there has to be a mechanism for fault tolerance. And what that means is if I have a distributed system of multiple servers, it's likely that one of those servers could fail during the execution of my processing. So Hadoop has a system for detecting that failure and then restarting the process. It doesn't have to restart the entire process from scratch. It would be restarting that portion of the process on the server that failed. MongoDB is similar to Hadoop in the sense that it has fault tolerance, but the requirements of MongoDB are that it be highly available, meaning that it takes automatic action to keep the database up and operable. So MongoDB has the requirement to be available to your application servers. It has to have uptime, maximizing uptime, in addition to fault tolerance. And of course, Hadoop is, again, based on doing batch processing across large amounts of your data set. MongoDB, as a database, will allow you to mutate data, do what's called fine-grained operations, which means I can perform operations on a number of documents or records, or I can do a specific operation on a single document. Hadoop is not designed to do fine-grained operations. Again, we're doing processing against a large amount of data. MongoDB is something that you would use with processing of your business logic. Okay, so some other things about MongoDB and Hadoop. The kind of workloads that we're going to be doing here are, again, offline processing, analytics, and data warehousing, whereas MongoDB is going to be something that interfaces with your application. It can be an application-based database, an operational database. The kind of architecture that these systems, that we're going to link these systems together is demonstrated in this slide. The idea is that your application servers or some kind of application client is going to be performing operations against MongoDB in real time. These could be CRUD operations. These could be a read-heavy system. It could be logging, logging events coming into the servers. All that happens first in MongoDB, where we're servicing our business logic. And then we're going to be exporting data. Either we're going to use the connector to export data to batch processing in Hadoop on the back end, or we can use the Hadoop connector to do iterative processing. The answer to the question is yes, this webinar is going to be recorded and available on the website, Joseph asks. And one note I wanted to make, feel free to ask questions. I'm going to try and keep the flow of the webinar moving forward so that I can address your questions at the end, so that we get through the material, and then I'll be happy to address all your questions. Okay. Another way that we can use MongoDB is it acts as what's called an operational store just ahead of this analytics layer. This is the case that we have data coming in from a very large system of many different database technologies, many different application servers, and we need a kind of central hub to aggregate and call all that data before it goes into Hadoop. That's another architecture that we commonly see out there. And MongoDB does a great job of that because of the flexible schema. We can ingest a lot of different types of data that will eventually go into Hadoop for its processing. So the use cases. Why would I want to use Hadoop? The things that we're probably going to want to look for, the most often performed analytics are going to be things like behavioral analytics. This means, do I understand how people are interacting with my website, for instance? Is my website navigable? Do I understand how my users use my website or my product? Is there something about my users that their behavior indicates interest that I can gauge? Am I servicing those users well? The other notion that we can derive from this kind of processing is understanding what's called segmentation, or basically understanding who my users actually are, what their age is, what their maybe their professional status is. If I'm a website that is in service to coders and a technology website, do I understand who my segmentation is? Are we talking about CTO level guys, people, or are we talking about maybe low-level coders? Another part of the analysis that I can do with this system is fraud detection. I can go back and I can see if anybody is trying to insert erroneous data or perform transactions that are attempting to do any kind of fraud on the system. And then we get into more sophisticated analytics like prediction. What will happen in the future based on prior data? So there's lots of stuff that we can do with Hadoop based on this idea. This kind of processing is not something that we're going to do real time on the database. This kind of processing is much more heavyweight. It might require multiple passes across the database, the data set that we have. So when we're talking about real-time versus offline, real-time is usually when we think about real-time processing, the results come back within milliseconds. Offline processing could take several seconds, maybe several minutes, depending on the data set that we're working on and the complexity of the analysis that we're using. So Hadoop is great for that. For real-time processing, we're going to use much simpler processing in MongoDB, perhaps with the aggregation framework, and examples of that would be averages and sums, counts. basic layout of how things connect together in an architecture, let's talk about how Hadoop actually works, what it does. And the best way that I know how to talk about a technology is to use an example. In this case, we're going to have an application that is ingesting sensor data or sensor logs. Very simple document structure. We see an example here of an individual sensor, a transducer, that passes in its data through the application servers, and it will be sent into MongoDB. This is a document that describes one sensor sample. And in it, you see I have got the underscore ID that uniquely identifies this particular sample. I have the device ID that says which sensor sent in this data, the actual value, the sampling value, and a timestamp and location data about where the sensor was when it took this data, the sample, and what time that the sample was made. Okay, so this is fairly simple, an easy schema for us to reason about. Now I want to perform some kind of analytics on this data. I will have perhaps thousands of sensors deployed around the world, and each of those sensors are taking in, let's imagine that this is a weather information, for instance. These sensors are going to be sending in samples perhaps many times a second. So the volume of data that I'm dealing with is going to be quite large. And for me to really understand patterns about my data, I'm going to have to process all of the sensor data that I've ever collected over the entire time that I've been using. I've had these sensors deployed. So to keep it simple, we're going to use, for example, the processing that we wish to do here is we want to find the average values by device, meaning that can we calibrate what this particular device's mean reading is to see if there's any particular nuances to this device, bias that this device has in its reporting. And we're also going to want to figure out what our sensor samples are telling us based on timestamp. If this is a weather sample, this transducer is giving us temperature, for instance. It's likely that the temperature being recorded is correlated closely, tightly, to the time of day. Daylight hours will mean that the temperature rises. Nighttime hours are going to be colder, and we can find that by this average the value by the timestamp bucket. And then finally, what is the average value that we can find for a location, an area? Okay, so one sensor sends in this sample, but we want to find out the correlation of what are the average values by the device, by the time at which the sample was made, and the location by which the sample is made. All right, to process this in an effective manner with Hadoop, we need a strategy, and that strategy is called MapReduce. What happens with MapReduce is it's a two-phase processing system. It's a strategy for processing data in a parallelizable fashion, meaning that I'm going to do very simple calculations, very simple processing across many parallel servers. I'm going to use that cluster of commodity hardware to divide up the processing problem, distribute the problem evenly across all of those available servers, and have them work in parallel with one another. So MapReduce has two phases. In order to perform a MapReduce function, I need to have a mapper function that you see here described on the right. And what's happening here, a map function does just that. It takes an input document, a key value store, and then it's going to map that into a new form of a key value store. I'll show you exactly how that works. See, the arrow there is the position of my mapper function as it goes through my complete data set. On the left, the square boxes, the rectangles, the green rectangles represent the data that I have in my database or in Hadoop. So I'm going to process one record, for example, and I emit 3 documents by processing this one document. The first document that I emit is going to have the key of the device ID and the value. That's what emits out here. The next thing that I emit is a subdocument where its zone or location, I have a bucketing function that you can see there on the right that buckets, takes the sensor's position in coordinates and then buckets it into a zone, and then I emit that with the value. And then finally, I do time bucketing, that for a given hour, these are the average values that happen at this hour. I perform the same operation across all of my data, and I start getting these emitted documents, which are grouped together by this key that I put in the emitted document. An example of one of these would be the common key that this particular group has is the zone identifier, where the location bucket. Another record in that same group shares the grouping key. We're still talking about zone A, but it's a different sample from a different sensor. And then the third one is, again, the same zone, but a different sample value from a different sensor. So I'm starting to group together these values. And in the next bucket, the grouping key will be the time bucket, when this sensor reported in at this time. Different sensors with different values, but they're all grouped by the same time bucket. Once I've grouped stuff like that, I can move into the second phase of MapReduce, which is the reducer function. The reducer function takes these groups that I've made in the mapping phase, and then in this case, very simply, will sum the values and increment a counter so that I can then divide the value by the counter to get the average. Now, the point of this is not to show mathematical complexity in the algorithm. The idea is to use a very simple mathematic problem here. Averaging is pretty easy to grok. The idea is to show how the mechanism of MapReduce works. And then finally, I can run this reducer function against each of these groups, reducing the problem space down to my final aggregate solve, what the average is for each of these values. But that's MapReduce. That's the strategy. That's the idea. I'm going to take a big problem. I'm going to divide it into small problems such that those small problems can be solved in parallel across a cluster of servers. That brings us to the architecture and ecosystem of MapReduce and the system that we're going to need to support to perform this operation. So if we start at the bottom of this picture, this stack, we're going to see something called HDFS. Okay. What HDFS is, the Hadoop distributed file system. The idea here is that if I'm going to process data across multiple nodes, I need a way of managing the data itself on these systems, on these dispersed systems. So that's HDFS. It's going to handle the data for us. On top of that, I'm going to use Yarn, which is yet another resource negotiator. Yarn is the system that manages the task itself of processing the data. So at the lowest level, I have the management of the data, storage of the data. Yarn is the distributed, coordinated task of processing it just above it. And above that, I have the strategies by which I'm going to process my data. MapReduce is one of the strategies that we just saw. There's also Spark. Spark is a newer technology that is showing a lot of promise and a lot of buzz behind it, and not without good reason. It's an exciting new technology. And still, again, at the highest level, I have domain-specific languages, DSLs, such as Pig and Hive, which make it easy for me to write MapReduce jobs because they provide an abstraction on the MapReduce strategy. So just to do a quick recap here, the base of the common part, the common technology in Hadoop is HDFS and Yarn. We have the Hadoop distributed file system, which manages the data, and then we have Yarn, which is responsible for the processing of the data. So in my Hadoop cluster, if I actually look at the architecture, let's examine HDFS. I am a client, and I wish to read and write data to HDFS system. This is going to be a huge amount of data, so it's likely that I'm going to need more than one data node. I need a cluster of data nodes to put my data on. And again, because I'm dealing with a cluster and I have a need to be fault tolerant, I want to have a system of replication such that if I lose one data node, that's okay. I can recover from that because anything I wrote to one data node is replicated to an adjacent node. So I get this redundancy of data and resilience of the system. But anytime that I deal with data that's distributed over a cluster of servers, management and knowing where the data is on which node shouldn't be a responsibility of the client application. It just wants to work with the file system. It doesn't need to know how the file system is organized. The job of managing the organization of the file system and the metadata is that green box at the top called the name node. And the client application, when it wants to get data from HDFS, will coordinate its efforts with get its metadata from the name node. Now that we have access to the data itself, we need a way of handling the task that's going to happen, the task that we wish to distribute across the system. So in this case, the client, the Hadoop client, wants to execute a task. It makes a request to the resource manager, and the resource manager will then create an application master. The application master is like a project manager. And the idea here is that there's one application master for every Hadoop task that the client requests. Once the resource manager has created an application master, the application master gets tickets or containers, not to be confused with the Docker container. A container is the terminology for a allocation of resources. It means I'm allowed to allocate this much CPU, memory, or disk. The resource manager has given me this allocation ticket. And the application master then hands the node manager the container ticket, and the node manager says, great, okay, you can have these resources. So what's happening here is the application master handles the specific processing of the data that the job that I want to run. But I need to coordinate the resources across this set of compute nodes, this distributed set, this cluster of compute nodes, with the resource manager and the individual node managers to get the processing that I want done accomplished. And that's basically what's happening here. Now, you might notice that in addition to HDFS and Yarn, when we start thinking about how these systems work, there's a great deal of complexity at hand here. And managing a Hadoop cluster is not for the faint of heart. It can, of course, can be done, but it can be a little bit challenging to get your cluster up and working. So that's why I'm going into detail with this, is so that you guys understand how these components work together. Okay. So how do we use the connector? If we've seen how Hadoop, HDFS, and Yarn work together to accomplish this management of data and the processing across the cluster, how do I connect this into MongoDB? Well, the connector is, we provide the connector. You can build it from the GitHub source repo. It's open source. We also provide jars or releases so that you don't have to build it if you don't want to. You can just download the jar. But as we saw in the earlier MapReduce example, I'm going to need to make a mapper class and a reducer class to perform the two phases of MapReduce. Hadoop and the connector jar itself is, as you can probably derive here, written in Java. So if I want to do MapReduce natively, I would be executing it. I would be writing my functions in Java and creating the mapper and the reducer class. Once I have these things, I need to make sure that the system is properly configured so that the resource allocator, the resource manager that we saw in Yarn, knows where to get the data that it needs to process from. So stepping back for a moment here, normally Hadoop processes, the Yarn controller processes the task, the data sourced from HDFS. In this case, we're going to do something kind of interesting. We're not going to get data from HDFS. We're going to get it from MongoDB instead. So HDFS is supplanted by MongoDB as the source of data that we're going to process. And that's what this configuration shows. You can see that there's a mongo.input.URI. That's a MongoDB URI of the database I wish the Hadoop to connect to get its data that it will process. And I can, after I've completed my processing, I can pump the results back into the database with the output configuration if I choose to. Now, it's all about flexibility. So in addition to getting data out of MongoDB and back into it, I can also do input and output on BSON dumps, which are binary output files that you can dump from MongoDB. So I don't actually have to connect directly to the database if I don't want to. I may want to create a dump file and then perform my MapReduce Hadoop processing against the BSON file and isolate the database from any kind of load that the Hadoop processing would put. So in this case, we take that jar, the Hadoop connector jar, and we hand it over to the resource manager. So the resource manager knows how to connect to MongoDB and how to get the data that it needs to process, which it will send to the compute nodes to be crunched. We, of course, write our own MapReduce job that's relevant to the kind of processing that we want to do, and we hand that over to the client execution. We use the binary Hadoop to execute my job.jar. It's what I've written. So with these two pieces of code, or two jars, I can execute my MapReduce task against MongoDB. So the way that this kind of connects together is you can think of, in this case, let's say we have a sharded cluster. I have my normal client on the right, and I'm doing my CRUD operations into the database. Hadoop is going to act like a client of the sharded cluster itself and interface through MongoS. Hadoop is getting its data or returning its data or its output to the database through MongoS. Okay, so the way that, there's some nuances here. The way that data is processed on the compute nodes for Hadoop is what's called input splits. No one processing node should get one giant blob of data to process, so we split up the input data so that we can send it to each of these compute nodes and get the benefit of all of these parallel servers. What the connector is actually doing is a kind of a clever thing, is when I'm taking data from MongoDB, it's going to use what we use, the unit of data that we use for balancing data across the shards, the chunk. We're going to map the chunks on a shard as input splits to the cluster. It's a really easy thing for us to do. We need to get data out evenly across all of the compute nodes in Hadoop, so we'll use the same mechanism internally to MongoDB that we use to make sure that data is distributed across all of our shards in an even way. And the system that does this, the part of the MongoDB Hadoop connector that does this, is the Mongo Splitter class. And there's a number of ways that you can, it calculates the splits and then send these input splits portions to the cluster to be processed. The Mongo Splitter class, or concrete implementations of the Mongo Splitter class, there can be different ways that you do this. You can use the existing chunks on the system, or you could, if you're not on a sharded system, you're a single replica set or standalone node, you don't have any chunks defined, you can use the same algorithm that would be used to calculate chunks on MongoDB to create the splits on the fly from the database to be sent to the Hadoop cluster. So there's a lot of different strategies by which you can send input splits into the database, whether or not you're on a sharded system or not. Okay, so I myself am a Java guy, but I am told that out in the world there are developers who are not necessarily Java guys. There's lots of great languages out there, all sorts of things. And it is pretty complicated. It can be pretty daunting to write a MapReduce task in Java. It's not the easiest thing in the world. That takes us into these special kind of domain-specific languages such as Pig and Hive. The way that Pig and Hive, remember from our stack before, our technology stack, that Pig and Hive were sitting at the top of that stack. The problem that Pig and Hive solve is that this language is a much easier language to deal with than, say, Java. It makes executing MapReduce, writing MapReduce problems or tasks in Hadoop much easier because the syntax is much simpler. You can create user-defined functions, and allows you to execute multiple MapReduce tasks iteratively on your data for those kinds of processing that requires multiple passes. And here's what a pig script would look like for doing an average. Pretty simple stuff. This is one average on the samples grouped. I believe on this one it was grouping by the device ID. The portions of this task, and this is the pig script in its entirety. It's very, very simple. I could do this, of course, in Java, but for those of you that have experience in Java, it would be a lot more code. It would be harder to read. It would be much more verbose in its syntax. Nothing wrong with that. It's just this is a much easier to deal with syntax, easier to reason about. In fact, when I teach the course, when I teach the workshop, we spend a lot of time trying to write this kind of averaging in Java. Once we move into the pig arena, it's much easier. The course goes much faster because this is an easier syntax to deal with. The portion in blue indicates the classes that were the user-defined functions that we've made in the connector that allow you to load data from MongoDB or store your results into MongoDB for closed-loop processing. Hive is similar. Hive is a subset of SQL, so it's an SQL-like language, and it's used for data scientists that are more familiar, or business intelligence professionals that are more familiar with SQL, and it provides that kind of an abstraction to Hadoop. But there's a little bit of a trap with both of these languages. Remember I was saying that these languages can provide an abstraction that allows you to process iteratively multiple MapReduce passes against the data. Each time I do that, I'm going to have to pull data from the disk on each of these distributed systems, and that can induce quite a deal of heavy I/O bandwidth saturation on the system. So there's yet again another strategy called Spark, a new technology for processing data on Hadoop clusters. The main advantage of Spark, it has in my opinion, two major killer app functionality to it. One is it's very easy to use. The syntax is very clean. It's very simple. So everything that it has the same benefit of Pig and Hive is that it's a very simple language to deal with. Two is it has a caching layer. Hadoop and HDFS don't cache data in any kind of memory RAM. So every time I ask for data to be processed off of HDFS, I'm pulling it off of disk, which can be slow. Spark allows you to cache data for intermittent results or the types of analysis that are multipass. An example of multipass processing would be the famous page rank that Google used for saying which page was most relevant. This is the old format when Google was young. Page ranking requires multiple passes across the data to get the proper ranking of pages. So those kinds of processes are going to be much more efficiently executed if you have a caching layer with hot data. Spark provides that for you. So Spark is, in just the last year alone, has really started to pick up in its popularity. I think it's possible that this could even replace MapReduce as a strategy, but it is still tightly used with Hadoop itself and HDFS, and Spark even uses Yarn itself for processing data across the set. So it's still associated with Hadoop. It's not necessarily going to replace all of the Hadoop ecosystem, but I think that this is going to be the way forward very soon in the future. And that is why we also allow you to use the Hadoop connector with Spark as well as everything else that we've talked about today. We can use the Hadoop connector to get data in and out of MongoDB to be processed by Spark or through a pig script or through native MapReduce and HDFS in Java or Hive. There's lots of different ways that I can flow data. And then, of course, not forgetting the fact that I can process off of BSON files. Why would I want to do that type of thing? Well, consider that if I'm doing heavyweight processing and analysis that requires that I go through my entire data set, if I ask my database to give me all of the data that it has, it could induce a lot of I/O. It could induce a lot of resource contention on the database itself. If that database, at the same time that it's trying to give Hadoop all the data that it has to be processed, at the same time also has to service an upstream application client, you can see the heavyweight processing that the database has to fulfill, has to provide, has an effect, a detrimental effect on the upstream application servers. They're getting bogged down because the database is working so hard. So in those conditions, what you might want to do is use a dump of the database, an incremental dump into a BSON file, and then you can use the Hadoop connector to connect up to the BSON file and perform your operations there, perform your processing at that point. And of course, one of the best benefits about the Hadoop connector is, of course, the ability to put those results back into the database. And that's the idea that once I get this closed loop processing, I can get the results and action on them very quickly back into the operational database so that whatever business intelligence or logic that I have upstream of the database can now make benefit of the processing, this analytics that I've done back into the database and action on those results immediately. So that's basically the Hadoop connector and how it works all together and the things that are available for you to use. There's a lot of stuff going on with this kind of a system. It's not a trivial architecture. It's not impossible to learn, but I would encourage everyone to give it a try. And feel free to ping me on Twitter. My handle is BlimpYacht, and I'll help you. I want to see people test this out and try stuff, and I'm going to continue to work on improving the workshop and helping people understand how to use the connector in an easy way, because there's a lot of potential here. But sometimes we all need a little bit of help getting Hadoop up and running. So feel free to contact me, and I'll respond to you as fast as I can. So let's take some questions. And I thank you for everybody who has had the patience of submitting the questions. I'll answer them now. Thank you for that. I just wanted to get through that amount of data as fast as I could. So let me go back here. Fahad asked, is MongoDB a database or not? I would say yes, it is a very much a database, a very good database. Yinzi, and please apologize if I have trouble pronouncing your name, could you please further clarify how Hadoop and MongoDB connector works? Just to do a quick summation is the task that's being executed in a Hadoop cluster is coordinated by the resource manager. So we're essentially saying to the resource manager, hey, don't get data from HDFS, get it from MongoDB. In fact, I would encourage people to go check out the code of the Hadoop connector. It's actually pretty readable, pretty simple. So you can see that in action. Ernani asks, considering we have to output files JSON and BSON, how is the better to work with HDFS processing? My doubt is if I have much difference between JSON and Parquet process performance, files perform better. Performance of reading I/O and files depends on a lot of factors. Some of them can be the I/O bandwidth and things involved with this disk subsystem layer. All things being equal, what we're trying to do here is have an integration between your database, your operational database, and the processing system that you have on the back end. We want to make it easy for these things to play well together in your overall architecture. That's the notion here. So there's different ways that you can integrate these systems together with the Hadoop connector. But it's integrating systems that require kind of the exchange of this data, and the value is that you're you're having a tool chain that works well together, so that the analogy that I use is MongoDB is the conscious mind doing the work, making sure everything happens. And your processing layer, like Hadoop, is the dreaming mind, where insights are derived offline when you're not doing work. And having that processing inform the conscious mind helps you do better work in your business layer. So that's the notion here. There's many different ways to use it, but essentially the idea is that we want to make sure that we have a good, strong integration between these two technologies. What else do we have here? There might be some typos. Somebody was asking counter 1 in the beginning and not 0. That's just the case that the counter is already initialized as 0. There was a possible grammatical error that I had in my slides. I'll make sure that I go back them one more time and make sure there's no confusing grammatical errors that I introduced. This is a good question. How is HDFS different from RAID systems? Fahad asks this. RAID systems are a redundant array of independent disks. And the RAID system is on a single server, essentially. If you're RAIDing disks, it's on a single server. You're increasing, possibly, depending on the RAID configuration, the bandwidth, but it's a single file system that you see on a single server. HDFS is distributed across multiple servers. So you could have a RAID system being the underlying storage system for a server, and that server is also part of a HDFS cluster. So RAID is just a storage technology. HDFS is a distributed file systems solution. Okay, let's see here. What else do we have? These are good questions, by the way. This is a good question from Tim, who asks, what does the use case look like when trying to use Elastic MapReduce on AWS? It looks good. The idea here is that there's a number of different ways that we can build our Hadoop cluster. We can use Elastic MapReduce on AWS. We could use Cloudera is another way of doing those things. I want to go and provide some examples of how to use Cloudera and Elastic MapReduce. We do have some on our MongoDB.org documentation that shows how to use those use cases. I'd like to further have more of that stuff available for you guys to use in the future. I like working in the pipes, so I've been hammering out setting up a file system, HDFS file system on the server itself. But Elastic MapReduce and hosted systems like Cloudera that provide Hadoop as a service, we work well with those systems as well. The benefit being that you don't have to manage those clusters. Cloudera, AWS does, and the connector will work fine with them as well. And then when you're done with those clusters, you can even retire them. You don't have to buy the infrastructure. The AWS provides them for you. Let's see here. Any tips for, this is a good question too, Kevin Brady asks, any tips for improving write performance for Hadoop output data back into MongoDB? This depends on a lot of factors. It depends on the type of writes, the volumes of the writes, how heavily indexed the writes that are coming back in. Generally speaking, though, I don't think that you're going to have too much trouble getting the output of Hadoop into MongoDB, because if you're performing processing, you're taking a lot of data to come up with a succinct answer to your processing problem. So in the case that we're doing an average, I may have gone through lots of data. I may have read a lot of data to come up with an average. But once I have that average, that's actually small data. That's a small data result set. So writing back results into MongoDB is going to be pretty lightweight. It's going to be asymmetrical. The read portion is going to be more heavyweight than the write portion. Although you can use the Hadoop connector to ingest data from HDFS as a means to seeding the data. So you can pull data from HDFS and put it into MongoDB. That would be like initializing, doing a batch import into the database, and that can be a heavyweight process. That's data ingestion, and there's lots of variables that are surround that. But that's almost like a webinar for another day. But it depends on how heavily indexed is their production load on the system, how much can we quantify that the right operation is causing in resource allocation, and all that good stuff. What advantages are there, Brian asks, what advantages are there to using Mongo in the stack versus running operations just through Hadoop? Well, Hadoop is not real-time. It's offline processing. There's no, and it's using what's called coarse-grained operations. A database is it gives you the ability to change and mutate data, not just on all of the data, but for individual records. So it's a different kind of problem space. One doesn't replace another. When we replace HDFS, this is a good question too. And Anil Kumar asks, when we replace HDFS with MongoDB, then aren't we losing the benefit of HDFS? Not necessarily. What you're gaining, actually, is the processing power of and parallelism of Hadoop. Essentially, you're getting access to a library of machine learning algorithms that are out there that you don't have to write yourself, like Mahout, Apache Mahout. There's SystemML, which is IBM's machine learning library. So having the connector allows you to leverage those libraries to do very interesting processing against the data in MongoDB. What you're gaining by using MongoDB in lieu of HDFS, you're still using Yarn to coordinate the processing, and you're using all the libraries I mentioned, but you're getting rid of potentially getting rid of the HDFS file system. The benefit is that you've reduced the overall complexity of your entire architecture. If I have data in MongoDB that's in the terabyte scale, not necessarily in the petabyte scale, I don't necessarily need HDFS. It may be the case that I don't need HDFS. All the data is in MongoDB anyway, so I don't need to have this second set of clusters to have this data that would be replicated or duplicated from MongoDB into HDFS. But that depends on your use case, whether you want to do that or not. I think that's a very compelling reason to use MongoDB instead of HDFS if you're at the terabyte scale. In fact, I want to do more operations to quantify the efficiency of doing such a thing. There's more work coming with regard to giving you actual numbers about when and use cases that this makes a lot of sense. So I think that question is a very good one, and one that I want to do a little bit more research myself. So be sure to check out my Brian. I should have put it here. My blog is brianranero.com, and for updates on that kind of learning, and maybe a future webinar about that as well. Are we out of time? Well, thank you everyone for participating. I really appreciate your value, the value of your time. And I'm sorry I couldn't get to all of the questions. They were excellent questions. But ping me at Blimpiot on Twitter. I will respond as fast as I can, and I'm happy to be of help to you guys. And go out and try this. It's a lot of fun. Thanks very much.